Alrighty, everybody, welcome into this screencast. Today we're going to talk about measurement, and one of the things that we're going to talk about is we're going to talk about this next concept, which is significant figures. Okay, now sig figs are often difficult for people to understand as to why they're important in chemistry, and one of the reasons they're important is they actually go back to measurement. So if you measure something to be, let's say, 2.5 grams, right? What you're saying is that the 2.5 tells you that your measurement is precise to the nearest tenth of a gram. Okay, so that's that 0.5. If you write that I measured, let's say I measured my solid in the lab to be 2.500 grams, okay? It means that your measurement is even more precise than this measurement over here to the left, and that you have measured to even more precision what the mass of that stuff is. So I told you in the classroom how we have balances that go out to the 100th place, and that those balances are hundreds of dollars more expensive than a balance that goes out to only the 10th place, like this measurement to the left, okay? So by including these zeros in our number, if we report out a measurement as 2.500, what we're saying is we are pretty darn sure to the tenths, hundredths, and thousandths place as to how much stuff is on that balance. And that is a significant statement, no pun intended, okay? So we're measuring to the thousandth of a gram here versus the tenth. And so in chemistry, we need to know how many sig figs we're dealing with, as that kind of helps us make sure that we're being accurate in our experiments and actually communicating scientifically how much stuff we're working with. So to get us kind of doing that, we need to go through the rules of significant figures, okay? So the first rule of sig figs, and when we start counting these, we're going to go through one of the four rules that we're going to say in our class to help us kind of spot how many sig figs are in a number or in a measurement, okay? So first thing is all non-zero numbers are significant, okay? I'm going to highlight things in green that are significant and underline. And so this whole number 613 is composed of three significant figures. Okay, 6, 1, and 3 are all non-zeros, meaning they're not zero, meaning each one of those numbers are a significant digit in that measurement. Same with the number 1, 2, 3, 4, 5, 6. Okay, so if it's not a zero, that's a significant figure. So in the number 10, right, if I just report my measurement just like that, I am saying that the only significant digit in that number is this 1, so I would have 1 sig fig in 10. The next rule for significant figures is what we call the sandwich rule, okay? So in a sandwich, we have bread, 2 pieces ideally, with stuff in the middle. In the sandwich rule, we have 2 non-zero sig figs on either side. That's like the outside of your sandwich, and on the inside of your sandwich are these zeros. So sandwich zeros, like these 2 double zeros here, are called sandwich zeros because they are sandwiched between 2 sig figs. In this case, it's 5 and 4. Okay, so this whole number has 4 sig figs. So the zeros in the middle become significant if they're in between 2 non-zeros. Okay, and just like in the cartoon Scooby-Doo, right? In Scooby-Doo, Shaggy and Scoob, zoinks, right, would make these really, really, really big sandwiches. Okay. So in chemistry, significant figures, we can have really, really, really big sandwiched zero numbers where all of these zeros here, there are 14 zeros, they're all significant because they are in between this 6 and this 2 here, okay? So what that means is any zero between 2 non-zero numbers is going to become significant. That's why this 602, this 0 is significant as well, okay? So sandwiched rule, right? Okay, so I'm going to highlight our non-zero significant digits in green and underline our significant zeros throughout this video. All right, right rule. Here's how this one works. Zeros are significant if they are to the right of another sig fig and to the right of a decimal point. And notice how I'm saying another sig fig here. It doesn't have to be a non-zero sig fig, just a sig fig. Okay, so 5.640 has 4 sig figs. What the heck is a right zero? Well, I see that there are 3 sig figs to start this number, 5, 6, and 4. This 0 all the way over here, right? This 0 is significant because it's to the right of this decimal point, and it is to the right of this 4. Now it also counts because it's to the right of this 6 as well. Okay, so you don't need to be immediately next to the sig fig for this to count for the right rule. The only stipulation is that this 0 is to the right of a decimal in the right direction, right? Not immediately next to it, but to the right of, and to the right of some sort of sig fig. So that could be the 6 or the 4. Okay, so that is our first sort of strategy here. All right, this one, now the bottom one, this big number, 1 and 2 are going to be significant, right? Because they are non-zero, so right off the bat, rule number 1, they're significant. However, these zeros are not significant here. These are what we call placeholder zeros because they are not to the right of a decimal. Yes, they are to the right of sig fig, 1 and 2, but they are not to the right of a decimal. Okay, so they are not going to be considered significant digits in this measurement. The last one that we have here is this is the only exception to this right rule. So 120,000, right? We have 1 and 2 right off the bat. Rule number 1, non-zeros are significant. However, all 6 of these are going to be significant because of this decimal at the end. This decimal at the end makes all of the numbers to the left of it significant. Okay, so this is the only exception. This is what I call the mic drop of chemistry. If you are to the left of a decimal or your number ends in a decimal, what that means is all numbers, I'm going to go hashtag for numbers, to left are significant. Okay, so that's the only exception to this rule right here. Okay, so if I end a number in a decimal, that means all digits that come to the left of it are significant themselves as well. All right, last rule is zeros to the left of non-zero digits are insignificant or they're just called placeholders. Okay, they're not counted as sig figs. So the first non-zero digit in this reading is the 4 that's bolded here. So these 3 are significant, making this number have 3 sig figs. These, underlined in red, are what we call our placeholder zeros. So I'm putting a P above them, okay? They are not right zeros. Even though they are to the right of this decimal, they are not to the right of a sig fig because this 0, right, is not significant. So in order to be a right 0, you have to be both the right of a 0 and the right of a significant figure. Okay, now this one has 2 sig figs, okay, the 5 and the 2. Again, these zeros right here are placeholders. Why are they placeholders? The reason they're placeholders is, again, they are not right or sandwiched zeros, okay? Yes, this is to the right of a decimal, but this 0, once again, is not significant. And placeholders can go on for a very long time, just like our sandwiches, okay? All these placeholders are telling us is they're telling us how big the number is, and this is a really small measurement. Okay, so that's what that abundance of zeros is showing us. Okay, so those are the 4 rules we're going to use. The last rule we're going to use is the rule for counting numbers. Okay, so exact numbers that we arrive to from counting, not measuring, not using a balance, not using a ruler, not using some sort of graduated cylinder, right, have what we call an infinite number of sig figs. Okay, meaning that they are exact out to infinity. Okay, so these counted numbers basically can only be whole numbers. They cannot possibly have a decimal fraction attached to them. So for instance, in my classroom, let's say I have 5 students there, right? That has an infinite number of sig figs. 5 students is infinite, and we can draw the infinity sign as like a sideways 8. That was a quite bad drawing there, but if I go a little bit more sideways, there's that infinity sign. The reason it's infinite is because in my classroom, if I have 5 students, I know for certainty, right? I don't need a measurement device to tell me that out to a million zeros, I know there's exactly 5 students standing there in front of me, okay? Now, if I had 0.6 of a student in my classroom, that would be another issue entirely, right? I cannot possibly have a fraction of a student. I can only have whole numbers of students. So let's just say in my classroom, there are 28 desks. I did not use a measurement device to find that out. Desks have to be complete in form. There's no such thing as a fraction of a desk. So again, that is infinity. You can write the infinity sign or you can go infinite, right? And write that as your answer. Okay, using these rules, let's go ahead and practice identifying sig figs with 1 through 8. So I'm going to do 1 through 8, and I'm going to take a pause here so that you guys can try these out on your own, and then we can come back and make sure we got the correct answer. All right, now that you've had some time to try and count these up, let's go ahead and see how we did. Okay, so 0.025. Here's 0.025. I see I have 2 non-zero digits, so rule number 1 says they're automatically significant. Okay, now we just need to decide on these zeros. These zeros right over here, they're not sandwiched, nor are they right, because there's no significant digit that they are to the right of, so we just have 2. This number right here, I know the comma's in the wrong spot. This number right here, right, again, we have a 5 and a 5 and a 9 here, so that gives us 3 at least. These zeros are sandwiched between these significant digits, so we're going to go with 6 sig figs, including every single one of those numbers there. 250, 2 sig figs with a 2 and the 5. This 0 here is not to the right of a decimal. Even though it is to the right of a sig fig, there's no decimal there. Okay, so that would just give us 2. If I wanted to make this an exact mic drop quantity, I could put a decimal there, and that would be 3 then. All right, 0.00909. Okay, so what we're going to do here is we're going to look. I see 3 placeholder zeros here. The reason they're placeholders is they're not sandwiched, and they are also not right zeros. That leaves us 9 and 9, so we should have at least 2. This 0 in the middle is actually interesting. You should notice that it's sandwiched between the 2 9s, and it is also a right 0 because it is to the right of this decimal right here and to the right of this 9. Okay, so that would give us 3 sig figs on there. All right, so here we go. This 0.008120. Okay, 8 and 1, hopefully you know that those are significant. The 2 as well. These zeros, again, just are placeholders. So if we have zeros to the left of the first non-zero digit, those will always be insignificant. Okay, and we don't count those. So zeros to the left of the non-zero digit, the first one you see in the number or measurement, are always not counted. This 0 right here, look at how and notice how it is to the right of this 2. Again, the right rule works by distance. The 1 and 8 also count for 0 being to the right of a sig fig, but it is also to the right of this decimal. Again, it can work by distance. So that is a right 0, making it significant. So we have 1, 2, 3, 4 sig figs. 4080, significant 4 and 8. We have a sandwiched 0 there. This 0, you may think it's to the right of 8, so maybe it's going to be a right, but there's no decimal there, so we're not going to count it. Just giving us 3. 7, 2, 0. This 0 right here and these zeros right here, are they significant? Well, hopefully you see that this double 0 is this sandwiched double 0 here. It is also right? These 2 zeros are rights because they're to the right of this decimal and to the right of the 7. Now this 0 at the end, also a right 0, okay, because it's to the right of a sig fig, being the 2 and to the right of a decimal. So that should give us a grand total of 5. Last but not least, when we have scientific notation, this might be a little tricky. We don't look at the times 10 to the part. All we do is we look to the part to the left. The part to the left is the first number in scientific notation. So if I look here, the 3 is significant. These 2 zeros are to the right of a decimal and to the right of the 3, making them right zeros. So that should give us a grand total of 3. Now, if you went ahead and you wrote this out in its decimal form, so you would have 30,000. You can report this. You could also report the sig figs here as just 1, because the only sig fig in that number is the 3, and the rest are placeholders. Okay, so you should be able to count there using those rules. The last thing I'm going to go over is the rule of multiplying and dividing. So how this works is when we're multiplying numbers together, the last thing we need to do with sig figs is be able to report our answer with the proper number of precision or significant figures. So when we're multiplying or dividing, basically what we do is the final calculated value will be the same as the quantity with the fewest number of sig figs used in the calculation. Okay, so what does that mean? So let's look at our first problem where we have a combination of multiplying and dividing of 27.2 times 15.63 divided by 1.846. This 27.2 has 3 sig figs. This has 4 sig figs, 15.63, because these are all non-zero digits. And this also has 4. Okay, so since 27.2 has 3, since 15.63 has 4, and since 1.846 has 4 sig figs as well, what that means is which of these numbers has the least number of sig figs? Take a second to think about it. Okay, hopefully you arrived to 27.2 being the least number. Okay, so since 27.2 has the lowest number of sig figs, your answer should only have 3 sig figs in it. Okay, so when we report our answer, what we're going to have to do is either round up or round down usually. Okay, so this is the answer your calculator will spit out when you put this into your calculator. So this would be 230.3011918. Okay, what you're going to need to be able to do is determine if you should round up or round down. Okay, the way we do that is we count up our digits that we're going to use in our answer, or how many sig figs. So we need 3 places or numerical places for 3 sig figs. So there's 230. What I'm going to do now is I'm going to look immediately to the right of my last decimal place, or my last numerical place. I see that there's a 0.3. What I'm going to do here is I'm going to go ahead and I'm going to look immediately to the right there. I see there's a 3 and there's a 0. So I'm going to decide what to do with the 0. Should I round it up or round it down? Since this is less than 0.5, right, what I'm going to do is I'm going to round it down and keep it at 230. Okay, so I should report my answer to something around 230. But I need to have 3 sig figs. Okay, so there's 2 ways I can fix this. The first way is I can put a decimal at the end of the 230, making this last 0 and everything to the left of it significant. Or I can report it in scientific notation. Okay, where I can say, all right, 2.30 times 10 to the second. This first part right here has 1, 2, 3 sig figs, because this 0 is right, to the right of a decimal and to the right of a sig fig. So that would allow me to have my answer in scientific notation with 3 sig figs. So sometimes when you're rounding and you get a weird number with a 0 at the end, to make sure you're reporting to the right number of sig figs, you might have to convert into scientific notation. Okay, so here's the calculation practice that I want us to go through, and I'm going to go through a few examples here just to make sure that we're all good to go on how we do this so that you can try the rest on your own. Okay, so when you're doing a calculation practice, you're going to be either tasked with multiplying some numbers together, plugging things in on your calculator, and then getting some sort of answer. What we're going to do on this section is we're just going to round up or round down based on the number of sig figs. So on this one, I see my first number, 287, has 3, 3 point is 2, 5.260 has 4. So what I always do is I always write the number of sig figs above my measurement, and then I choose the one that has the least number out of those. So I physically write this down so I can see it. I find that students have greater success on these problems when they actually write this down on top of it and choose the right number from there. Okay, so I see that 2 is the least number of sig figs in my problem. So with this 46, I got to look to see how I can round this up or round this down. So 46 has 1, 2 sig figs right off the bat, so I'm going to stop at the ones place for this rounding. What I'm going to do is I'm going to look immediately to the right of the ones place, and I'm going to see what I should do with the 6. Since I'm 0.7, that's above 0.5, I'm going to round this up and change this to 47. So this rounded answer to 2 sig figs is 47. 4 and 7 are both significant. All right, so that is my first one. Okay, pretty clean, pretty easy. Again, we got to get good at counting sig figs. I went really fast here and said this had 4. The reason this has 4 is because this is a right 0. Okay, so the right of the sig fig, right of the decimal. So you got to be able to count sig figs pretty quickly and get good at it as we go through this and do more practice problems in class. All right, so the next one, these 3, how many sig figs are in each? Why don't you go ahead and try to write it on your own and see if you get it right. So pause this video and check your work to see if you got it right. All right, so 4.8 times 10 to the 21st. Remember, we don't look at the times 10 to the part, so this is 2. 3.24, that is 3, right? And so we're going to go with 2 again. Looking at our answer, 1.5552 times 10 to the 15th. My first 2 sig figs are there, and now I'm at the 5, okay? So in chemistry, one of the weird things is how we round on 5s, okay? Typically, you've probably been told to round up. In chemistry, the tradition is to round down on a 5. In my class, I don't really care which direction you choose. I'm just going to go the chemical way today in this video and round down, so keep the 1.5. So I would say my answer is 1.5 times 10 to the 15th. So in my class, if you rounded this up to 1.6, that's fine. You know, it's one of those weird things, okay? So I'm going to go through and show you what the rest of this notes set entails. It has a few more of those problems, some counting problems, and then here you are going to convert some numbers into scientific notation like we did in the previous lessons, except the only sort of hiccup is now we're going to report them to the same number of sig figs. So for example, I'll do one of these with you. I see here I'm in decimal form. So since I'm in decimal form, what I'm going to do is I'm going to count up how many sig figs I have. So I have 1, 2 sig figs here. All right, so I'm going to make a significant or scientific notation here with 2 sig figs in its construction. So how am I going to do that? Well, I know that my number here in decimal form is greater than 10, right? That means that when I put this in scientific notation, my first number is between 1 and 10. So I'm going to put my decimal between the 2 and the 3 here. Then what I'm going to do is I'm going to multiply it by 10 to the something. In this case, since my decimal form number is greater than 10, my exponent will be positive. So I just need to find out how many places I hopped to move this decimal. So to move this decimal from the end of this number to between the 2 and the 3, whoops, I moved 1, 2, 3, 4 spots. So that would be 2.3 times 10 to the 4th. Okay. Now I'm just going to check to make sure that I have the golden number of 2 sig figs in my number, in my scientific notation. Oh, look, I do, because 2 and 3 are both significant. If I answer this as 2.30, right, this would not be correct because 2.30 has 3 sig figs with this right 0 right here. So 2.3 would be your proper answer. So that's what you're going to do with the rest of these numbers. Okay, so notice here how there's a whole lot of sig figs at the end. You're going to include all of those sig figs in your scientific notation answers. All right, so for the last part says to follow the previous directions. So for this ones, you're going to do some sort of calculations here. You're going to multiply these out, and then you're going to put them into scientific notation with the proper number of sig figs. Okay, so these will all spit out answers in decimal form, and then what you're going to do is make sure that you report it into scientific notation with the proper number of sig figs. If this comes out to a number that's between 1 and 10 already, I'm just going to show you one of them I know that's going to. So number 29, if you divide 36.000 by 6.000, your answer in the calculator will spit out to be like 6, obviously, because 36 divided by 6 is 6. I see here that I have 1, 2, 3, 4, 5 sig figs, as all of these are right zeros. I see here that I again have 4 sig figs with 3 right zeros. Okay. So what we're going to go ahead and do is we are going to report our answer of 6 with 4 significant figures because that's our least number of sig figs. So to do this, right, remember, if it's already between 1 and 10, we're going to report this as 6.000, because all of these are right zeros, giving us 4 sig figs, times, and if you remember, to make a number the same or keep it the same number, because this is already between 1 and 10, we don't want to make it bigger or smaller for scientific notation, we're going to multiply that by 10 to the 0, because 10 to the 0 is equal to 1. All right, well, I hope this was really helpful for each and every one of you who are watching here. Thank you so much. Enjoy.